to our colloquium, as usual. So our speaker today, within this school on water that we are running right now in ICTP-SAIFR, is Professor Paola Gallo from Roma 3, from Italy. And as usual, I'm going to introduce a little bit her. So she got the laurea in Física in, should I say, maybe, no, 1990. In La Sapienza. Then she got the PhD in 1994 in University dell'Aquila. And then, as usual, she had the postdoctoral training mostly in MIT for 2 years. After that, she came back to Roma and she started, let's say, all the procedure in order to stabilize. She was initially a postdoctor, and then she became an assistant professor, an associate professor, and from 2012, right, you are a full professor in Roma 3. Now, her expertise is about soft condensed matter and statistical mechanics and so on. And today she's going to talk about water and the others. Paola, the floor is yours.
Okay, thank you very much to everybody for coming here. It's really a pleasure to come to this place. It was very nice for me to come here. It's my first time here, the first time in Brazil also. I am enjoying the stay very much, also the school, of course, and today I'm going to present also this colloquium. I will do it with pleasure. And the title, Water and the Others, will become clearer as we proceed with the talk. This is the outline of the talk, and I study water. In particular, I study water supercooled, so water when it's kept liquid below its freezing point, so in a metastable state. Water has many anomalies, so I will talk about this phenomenology, the anomalies, the fact that it has 2 kinds of liquid, a low-density liquid and a high-density liquid, and we would say almost for sure now a second liquid-liquid critical point beside the usual liquid-gas critical point, and also a dynamics which is typical of a liquid undergoing a glass transition. I will talk about classical potential that I use, and then for the core of the seminar, I will do several examples on how water features are important. So I will briefly introduce the bulk feature, but then I will show how water features, also the bulk-like ones, are important when water is in solution with others. So others mean it can mean ion, can be in biomolecules. So I will show example of water in solution of electrolytes and perchlorates. These last one are interest for the recent discovery of water on Mars. And I will show what happens to the phase diagram of water when we put some perchlorates in it, what happens to the critical point, if it moves, if it disappears. And then in the second part of the core talk, I will talk about hydration water in biosolution. This is a line of research that is going on in my group since many years now. In all these things, I will present my latest results. And in particular, with this part, I will show analysis of dynamics, slow dynamics connected with the glass transition, and then study of local structure. And then I will show you the difference between bulk water and a solution with water and lysozyme, and bulk water and a solution with water, lysozyme, and trehalose. Lysozyme is a globular protein, and trehalose is a disaccharide. And these lines of research have interest in cryobiology. At last, if I have time, I will make another example of research of water with the others, which is the phenomenon of the brine rejection when water crystallizes and is in contact with a solution of ions. Some are spontaneously included, and a brine is rejected. And this inclusion, how many ions are inclusion, is important to study for life and also experiments that we are doing in outer planets like Jupiter. For example, now we have just sent out something on the icy moon of Jupiter and JUICE mission, and we will see something in some years from now, but in the meantime, we are also doing some research. And then for this I am collaborating with a colleague of mine who just got a big ERC grant for studying this kind of issues. And then at the end, if I have time, I will show you water and feldspar. Feldspar is abundant in the atmosphere, and this has relevance for ice formation in the atmospheres. I don't know if I have time, but I would like to. And then, of course, the conclusion. So a very brief crash course for those who are not familiar with the glass transition and glass transition. When I talk about supercooled liquid, I mean that I start from a liquid above the freezing or melting temperature, and then instead of following the equilibrium path that will drive me to the crystal phase, which is the only equilibrium phase of the crystal, I supercool the liquid and go in a metastable phase. So I take how can I distinguish between this path and this path? Simply taking away kinetic energy very fast from the liquid, so to avoid the bypass crystallization. So the liquid gets lower and lower and eventually freezes in a disordered form, which is a glass, at a temperature which is the glass transition temperature. Actually, what is the glass transition temperature is a bit in discussion among the group of theoreticians working on this zone, but from the experimental point of view, to give an operational definition, let's for now say that the glass transition temperature is the temperature in which the viscosity is equal to 10 to the 13 poise, and this is used also for technical comparison of different kinds of glasses. And then at this temperature, the glass has still some movement, so there is still ergodicity, while at the theoretical glass transition temperature, everything should be frozen and the system should be not ergodic any longer. But for the purpose of applications, this temperature is also very useful. But now let's go to supercooled water. So supercooled water, the supercooling of water toward the glass transition has some difficulties because this is water phase diagram in a region in which we have here the stable liquid. So this is the pressure, this is the temperature, this is the melting temperature. And in this region here, the yellow region below the melting, I can go with the experiments so in the supercooled space with no problem. At a certain point, this is an experimental limit. We have a homogeneous nucleation, and there is this part of the phase diagram in gray here, in which experiments have difficulties to go, although recently some of my colleagues that are very good experimentalists, especially the group in Sweden, are going down, are crashing inside this region. But anyway, we call this region no man's land because from the point of view of supercooled state, we cannot go there. Only ice exists here. Ice, yes, of course, the stable phase, but not the metastable phase. On the other part, we can have amorphous ice by compression. We can amorphize the crystal. And And then heating, we can arrive to a supercooled liquid here again, but still we have a limit in which it turns to crystal. But in this region here, since many years, experimentalists have seen that there are two kinds of amorphous phase, a high-density amorphous and a low-density amorphous. So here is the reverted phase diagram. What we think is that this first-order phase transition will go into this normal length to finish in a second-order critical point that in the two-phase region separates a high-density liquid from a low-density liquid, and later below, for lower temperature, a high-density amorphous from a low-density amorphous. This is the normal liquid-gas critical point that we all know that all the substances have, and this is another first-order line of transition, and this is second order, and this one should be second order too. And at least you will see for simulation, we know that this Ising universality class, both this it is, and also this. At least the simulation have rigorously proves for certain classical potential, this liquid critical point exists, and it's second order liquid critical point with belonging to the Ising universality class. Okay, experiment, as I was saying, are shrinking the region. For example, so this is one of the two papers came out, Kim et al. On Science 2017 and Science 2020. This is the group of Anders Nilsson, as I told you, a dear colleague of mine and a very, very good physicist that is doing really a very beautiful job with difficult experiments. Okay, water has many anomalies, and back when I started my research on water 30 years ago, people said, okay, there are divergences of, apparent divergences of these quantities, isothermal compressibility, constant pressure, specific heat. This in red that you see is the behavior of simple liquid. This is the behavior of water. These are the experiments here, KT and CP. So there was this divergence, not so big because the exponent is not so high, but still apparent divergence. We now know that this is not a divergence, but is the starting of a maximum. Okay, so specific heat and isothermal compressibility have maxima, and I will talk about this maxima now that I move to this other transparency. This is a paper that I wrote together. It's a review paper that I brought together with many friends and colleagues of a lifetime, a chemical review that is really exhaustive on the subject of supercool water and of these two liquids that it has. And this is another picture of the phase diagram, more complete now. This is the liquid gas critical point. This is the liquid critical point that we found in simulation, and that we have indirect confirmation of its existence from experiments. HDA and LDA is high-density amorphous, low-density amorphous. This line is first order. We have no man's land here, but in the ultra-viscous states, we had a high-density liquid and low-density liquid that was measured. I just want to, here in this region, in the stable phase, we have several kinds of ices. Water can have, is polymorphic, can have a lot of ice, and two amorphous phase, so it's polymorphic. And I wanted to spend still some words about this WL. This is a line which is called the Widom line. So in critical, from Ben Widom, which is a well-known statistical mechanics physicist, when you get close enough to a second-order critical point in the one-phase region, thermodynamic function, let me say, the correlation length starts having a maximum. So if you, for example, do an isobore and cross the Widom line, you will see that here we have a maximum of the correlation length. This maxima, as you, for example, decrease the pressure, form a line that points to the critical point. Okay, so in the case, for example, of supercritical water, I have a paper on Nature Communication in which we calculated the Widom line from experimental maxima of specific heat and isothermal compressibility for water. So, yeah.
Not in the field. If you say metastable, it means that after some time it may become stable.
Yes.
So what does it mean to say that at a certain time and temperature and pressure you have something metastable? So it has many possibilities and it depends how you get there? Is that how you say it?
Can you say again?
So you have, for example, LDA, LDL. Those are metastable.
Yes, yes.
So there can also be at that same temperature and pressure a stable state.
A crystal. You can have a crystal.
Okay, and how does it decide which is which? Does it depend
Yes,
on the
it depends.
path?
Yes, depends if I cool fast enough. As I was saying at the beginning, if I take off kinetic energy fast enough, then the liquid will not have the time to go to the equilibrium state. And thermal fluctuation will never allow that any longer. You have in the potential energy landscape one deep minimum, which is the crystal minimum, and many other relative minima. The system gets trapped in one of those minima and can change minima only with thermal fluctuation. But if you keep on taking off kinetic energy, supercooling the liquid, you will never have the energy to have a fluctuation to overcome this minima, and you will remain disordered, a glass.
Is there a way to quantify that, to say, for example, what the size of the potential is or something like that? Or is it just, we did this experiment and it got something?
No, glass transition is something that is ubiquitous in condensed matter. For example, your your window glass is silica, and that is a glass and was obtained exactly with the supercooling procedure, because that has a stable phase, which is a single crystal, but it's not the one of your window. So it's metastable. The crystal in the window is metastable. It will eventually become a crystal in a time that is superior to the age of the universe. So you understand that is, even if it has some little fluctuations, and you cannot say theoretically that it's really non-ergotic, it will never become a crystal. Did I answer your question?
I guess what I'm asking is, suppose somebody does an experiment and you want to tell them, are you going to get the metastable state or the stable state from your experiment?
Right.
So you have to tell them how to do...
how to cool.
Yeah, so is there a quantification of that you can tell them? If you...
Water has a very strong tendency to crystallize. So most of the time you get the crystal, unless you have a proper experimental apparatus. In your freezer, you have polycrystalline ice. And so you have to cool very fast. It's the cooling rate for water. And also the purity, because although it is an homogeneous nucleation, apparently the others trigger the ice formation. And so these are the two things most important that I would say: pure water and cool fast.
Okay, thanks.
And it's the same one that you have to use if you want to have, for example, when they got the quasi-crystal, they have to do this, I don't know how to say in English, we call it tempera in Italian, so temperaggio, so rotating this very fast and spitting this metal on it so that it could cool down very fast. You cannot do this in water, it's not a metal, but there are all these techniques to obtain super cooled or ordered phase of certain kind or others.
Okay, thanks.
Sure. Okay, so coming back to this Widom line, so this is the...
Paola, perhaps related to the question of Nathan. I mean, as you said, for glass, if you just cool once, you get the metastable, let's say. What is the time of cooling that will be necessary in water to see the supercooled?
The cooling rate?
Yeah. Well,
For the experimental cooling rate, I don't remember the number. I mean, they cool it as much as fast as they can, but the cooling rate, I don't know. With the computer simulation, we don't have that problem because our cooling rates, it's an order of magnitude larger than experiment. So we go to for us, it's more difficult to crystallize than to supercool. And in fact, that's why molecular dynamics simulation were very useful to help the experiment to back up the experiment because we get the supercool state easy enough.
Okay, thanks. Okay.
And let me go on again and with another explanation. I put all this transparency because there are a lot of people not in the field, otherwise you don't follow anything. And please stop me again if you have doubts, because otherwise it becomes less clear. It doesn't matter if I cannot present all my results. A few of them is going to be okay. What does it mean high density and low density water? So water is, as you might know, has a very strong tendency to form a local structure which is a pentamer, because the oxygen hybridizes as sp3. And then he has two covalent bonds with the hydrogens, and then is left with two lone pairs. So the covalent bonds of the hydrogen and the two lone pairs point to the vertex of a distorted tetrahedron in this way, okay? So lone pairs and hydrogens. And so they tend to get closer to other water molecules. The hydrogen is protonated because the electron is almost always close to the oxygen. So the nucleus is probabilistically more bare than other nuclei. That's why the hydrogen bond is so important, because the hydrogen has only one electron, and in water it gives the electron most of the time to the oxygen. So the hydrogen bond is a rather strong bond of the van der Waals kind. So, sorry, I have this problem with this. Okay, here it comes. So what happens is that, see, one single water molecule has a tendency to bind to other four molecules, okay? Making these basic pentamers. Of course, in the liquid, it breaks in reform, but this is a strong tendency that water has. That's why it's so easy for water to crystallize. And then the pentamer can approach each other in this more open way, and this is the low-density liquid, or in this other fashion, and the structure is more compact, and this is the high-density liquid. So I described this a bit in this science paper that I published with my friend and colleague Eugene Stanley from Boston University. And you see, this is always the phase diagram with the critical point, the Widom line. And this point of the Widom line was measured experimentally, that was the same before, by this experiment on Science of 2017. These two are other two special issues that I wrote this one is a special issue that I wrote on a PJA in 2021. That's also more recent and describe these things. And I also authored a special issue on Jake and Fis in 2019 on supercool water with Thomas Lerting and Francesco Shortino. And also this describes all these things if you're interested. Okay. So this is, since this was wide audience, this is also a talk about, this is also a description of what I do. I study classical molecular dynamics simulations, so the potential is classical, and the trajectories of the atoms are generating, integrating the equation of motion, the Newton equation of motion. This is a snapshot of a molecular dynamics simulation of liquid water at 298 Kelvin. And for systems that obey the ergodic hypothesis, time averages, as you know, are equivalent to ensemble average. So I can use the macroscopic thermodynamic properties, but also the dynamics of the system doing ensemble averages, substituting ensemble averages with the averages on the trajectory over time. So basically, by evolving the Newtonian equation of motion with the finite time, I can save a trajectory in space-time of my fluid in equilibrium, because all the physics that I'm going to present you is physics of equilibrium, and I calculate the average over time instead of doing the ensemble average. Okay. What kind of potential we use when we do this classical simulation to study all this phenomenology that I was discussing with you about on water? We use classic potential. These classic potential are of several kinds, but in order to study the slow dynamics, which take a certain amount of time, or you will also see extended region of the phase diagram, you need a transferable potential. So far, potential that are too sophisticated, polarizable, not rigid, machine learned potential from first principles, do not have this transferability in a large part of the phase diagram. So until today, still, the best potential is a simple one. So we take a rigid molecule. The best in this period is this T4Pi 2005 and T4Pi that were done by Carlos Vega and José Abascal in 2005. They're very good potential, rigid, and we have fractional charge on hydrogen and oxygen, but since these are effective potential, the charge of the oxygen with respect to the real molecule of water, it's a bit displaced. Instead here, in place of oxygen, we have a Lennard jump potential that is the one that you have to put in order to take into effect the fact that it's a classical potential, but you need some, you cannot crash. If you use only the Coulombic potential, of course, you would not have some repulsion, the repulsion that you would not have the hard core that you need. Otherwise, the particles crash on each other, because we are, of course, not dealing explicitly with quantum mechanics. We use a cubic self with periodic boundary condition when we simulate water, for example, in the bulk phase. I've studied water for many years, but I will present to you some results of water and the others, so water in solution with the ions and proteins. So let's start to look what happens when we look at the phase diagram of water. For example, this is a T4Pi, one of the two potentials that I just presented. This is a Jagan-Fiso 2001. This is how the phase diagram of water looks like. Okay, so these are isochords. Minima of isochords show you what is the temperature of maximum density. You know that if you that for water, this is famous, at 4 centigrade at ambient pressure, we have the temperature of maximum density. This is a very famous, is the most famous anomaly of water. Okay? But the temperature of maximum density change if you change pressure. We are at a constant pressure, for us is 4. But if you change pressure, it has a trend. So the temperature of maximum density line is this line here. And this is what we calculate for the bulk. And it extends from the normal to the supercooled phase. In the supercooled phase, these lines here that you see are maximum of isothermal compressibility, specific heat, and minima of coefficient of thermal expansion. At the end, they all converge to the Widom line that is converging to the critical point. This location of the critical point, you can use several indicators. The critical point can be found where isochord cross, okay? But also you can use a rigorous method of statistical mechanics to locate it with grand canonical Monte Carlo and finite size scaling. So for example, for T4PIs, there was a recent paper that found it rigorously here. So our indicators point to this point too, but this is a rigorous location that was found by Zerze, Shortino, and Pablo De Benedetti, Francesco Shortino, and Zerze on a science paper of 2021. Okay, so it's the shape so we can see in the Rotti the same phase diagram in the PT and in a Rotti phase, and I took off the isochord and I only left the important curves, thermodynamic curve. So this is the temperature of maximum density line. As you know, water has a maximum density, but then after a certain point, it arrives to a point in which it restores the normal behavior. So this is the temperature of minimum density line. That is done like this. This is the limit of mechanical stability that for a single phase fluid is also called the spinodal in thermodynamics. This means that if you so you see here you have positive and negative pressure, and experimentally you have positive pressure if you press, you have negative pressure if you squeeze, okay? So you leave the fluid with no air inside and you start with a piston to squeeze. The fluid remains liquid until a certain point, then it can't hold it no longer, and you have this, which is the spinodal or limit of mechanical stability. There is nothing here, okay? And in what happens is that the liquid separates in two phases, one liquid and one gas when you do the experiment. There's a question?
Can you run the simulations for lower temperatures and access, for instance, in the coexistent region? Can you run your simulation for lower temperatures and, for instance, look at the behavior of the system in the coexistent region, for instance, in the liquid, high density and low density liquid coexistent region?
This is a limitation of molecular dynamic simulation. At a certain point, I cannot equilibrate any longer, because when I arrive to the potential energy and escape limit and I go below, then with simulation, this starts being history dependent. If I want it not to be history dependent, I have to change technique. And then I have to do rapid quench with steepest descent, algorithm that search for the minima. I cannot leave it like molecular dynamics, Newtonian equation of motion. So this simulation here, I stop to my limit. So for example, when I don't know whether I will present the data or not later on, but I've seen that when I had the ions, this extends my power of supercooling with molecular dynamic simulation. So I could access also the low density and high density phase regions, okay. The two phase region. But if you see that I stop because I cannot go below with the simulation. Otherwise, I have to use other techniques. Okay, so this shape here shows the characteristic existence of a second critical point, and as I told you, this blue line, the exact rigorous location was proved by De Benedetti, Shortino, and Zerze in this science paper. This is a grand canonical Monte Carlo. I'm not sure they probably did the successive umbrella sampling. and which is a very nice technique to do these things, and the finite size scaling, of course, to locate the exact region and extrapolate to the infinite point. Okay. So, as I told you, water with the others are some difference of behavior. For example, now we are looking at the thermodynamics. For now, in the first part, I'm concentrating on the thermodynamics. So this is the same kind of simulation that I did for the bulk, only I added a lithium chloride aqueous solution. Of course, inside the solution, these become ions, so lithium plus and Cl chlorine minus. And for ions, I took this potential Madrid 2019, which was properly done 40 for P 2005 by the group of Carlos and José Luis with Zeron. And these are the parameters, but the potential is always the same. It's the Coulombic part with fractional charges and the Lennard-Jones. And these are the phase diagram for, we studied the two, in this paper that I'm illustrating now, we studied two concentration, 0.6 and 2 mol per kilo. This is more or less water, salty water concentration, and from that you can calculate this is 3 times, more than 3 times larger. And what we find is that we have the temperature of maximum density line that is changing a bit only for the larger concentration. And the liquid critical point for this lower concentration still exists. But when we supercool more, we couldn't find traces of liquid critical point, although I must say they might have shifted to lower temperature, although I don't think so, because this one is shifting. Yeah, shifting to slightly, actually, to higher temperature, so strange. It's probably canceled by the presence of the solution. But despite of that, you see that we still have, so this triangular, the Widom line, I must say this is a proxy for the Widom line. We use the KT. And isothermal compressibility. And this blue line also is a Widom line. So we have a Widom line also for the solution, but still we couldn't find the liquid critical point. But it is important to see that the peculiar characteristics of water are still present. And in particular, in all these solutions that I will show, if the concentration is mild, water keeps on having this low density, high density liquid, this interplay between these two structures. And this is always important for all the properties that our water has on our planet. So there were recent evidence of the existence of a pond of liquid water on Mars, on the South Pole Martian crust. This was a paper in 2018 by this group of geophysicists, part of which is in my university. And so we started to look at the concentration of studied the water with sodium perchlorate ions. These are ions inside water. And this is the perchlorate ions, the chlorine with the 4 oxygen. And we still use the T4P 2005. We studied 2 concentration, 2.43 times 10 to the minus 3 mole fraction. Oh, let's look at the weight concentration, 1.63 and 15.4. And this is a paper that we published in 2023. Still, we are interested to see whether there are and of what kind modification of the phase diagram. These are the phase diagram that we studied. I hope you can see them. And these are the isochords. So we have the C1, the lowest concentration here, the highest concentration here. We can see that this is the temperature of density line, and this this here is the critical point of the solution. This here that I'm pointing, even if you cannot see it's here, is the bulk critical point. So we have still a temperature density line for the lowest solution, and for the lowest solutions, we also have a liquid critical point, but it's very close to the bulk. But in this case, at variance with what happened for the lithium chlorine, here we still have a liquid critical point with the higher percentage in weight. As you see, it's shifting toward higher temperature and lower pressures. This is the comparison between the bulk, the lowest concentration, and the highest concentration. So in red, the bulk, and the TMD, and the liquid critical point. Sorry, not in red, in this blue. In red, the lowest concentration, so blue, the liquid critical point, red, the liquid critical point of the concentration, lower concentration, and this is the liquid critical point of the higher concentration, and the TMD, as you see, is substantially shifted. The limit of mechanical stability line is very similar for the three of them, bulk, C1, and C2 concentration. So what is happening at the end of the day in this solution? This solution is happening that when this is C1 and C2, what is happening is that there is a shrinkage of the low-density region upon increasing the concentration of ions. This is because low-density region is the mother of ice. That conformation that I showed you is similar to ice age. So if you have a low-density water, it's easier to make it crystallize. Low-density water tend to form ordered structure in which ions are not included. Okay? So when you increase the percentage of ions, the ions typically go to the high-density phase. And when it's a small amount, you still have, with respect to the bulk, a large enough low-density liquid phase. But when you add many ions, the high-density liquid region enlarges at the ends at the expenses of the low-density liquid phase. This is even more clear in another study that I did time ago. In fact, it was another potential of the TIP4P class, but less efficient than the other two, the TIP4P, in which I studied the bulk in NaCl solution. Since I am, how long do I have left? 15 minutes, right? Okay. Is that should I leave some time for questioning? 5 minutes, something. Yeah. Minutes. Okay. Okay. So let me skip this, because as I told you, let me just show you that in this paper on NaCl, you can see this thing that I was saying of the shrinkage of the low-density region of water, low-density liquid region of water. This is the bulk. This is concentration of NaCl 0.67, and this is the concentration of NaCl 1.36. So this is salty water. This is 1.36. This is 2.10. The liquid critical point is shifting to higher temperature and lower pressure, and the LDL, you can see it very well here, is shrinking. In this solution, it is nice that the LLSCP could be found, it stays. So we are showing that there is a substantial shrinkage, but also that the LLCP is still present. Why is water, a message out of this part, because now I'm going to show you in the rest of the talk something on dynamics. The message in this is this. Water, the message of this part is the following. Water wants to to stay with the other water and tends to exclude the others. That's why I say the others, because they're like strangers to her. And so what happens is that it's trying to preserve all the anomalies that she's got. And this is an important thing to keep always in mind when we study water together with, in many applications with other matter, that water wants to behave always like water until it can. So this is important to understand also from the biological point of view, some problems on the biological point of view. So we were talking about glass transition, and we showed that the water with the molecular dynamic simulation is undergoing a glass transition as predicted by a theory on supercooled glass transition, which is the Moe coupling theory. And in this paper, we showed that water was behaving according to the theory, and there was also experimental confirmation by this nature of Renato Torre and co-workers. And so water behaves according to Moe coupling in a region of mild supercooling, and I will show you in an next transparency what it means. And then after it changed to another regime in which we have only activated the processes, and then at the end we have a glass. Let me be more clear on that. Let me just show you. Okay, on the next slides. Okay, I'm going to show you results on the single particle dynamics. I'll show you a density correlator that correlates the density of a particle with the density of a particle at a certain point in the space-time, with the density of a particle at another point in space-time. Self, because it's the particle within self. In physics, we could study also the particle with the correlation with that particle with another particle, but not for these results that I'm showing you today. So in the direct space, it's called Banov correlation function. The Fourier transform is called the self-intermediate scattering function. And for a normal liquid, it relaxes with a stretched exponential, the self-intermediate scattering function. When you have a supercooled simple liquid, it has a first fast relaxation, then a plateau, and then a stretched exponential with an exponent here. Okay, so why do we have this difference between normal liquid, which will be water at room temperature, and a supercool liquid, simple liquid, like also water below the melting? The explanation is this. And follows the Moe coupling theory, which is a cage theory. At time equal to 0, I sit here on the particle, and my first neighbor, when I supercool, start having a very slow dynamics. So at time 0, I start with the ballistic motion, but then I feel the potential of the cage of the first neighbors that move very slowly. I rattle in this cage, and then when the cage relaxes, I can escape. So if I look at the mean square displacement, I have a ballistic behavior, then a plateau in which the particle rattles in the cage, and then the particle gets out of the cage, and this is the diffusive behavior predicted by Einstein in one of the famous 5 papers that he did in the 1905, the Brownian diffusion. Okay, so we have now that we are supercooling, we still have the Einstein prediction, but we have an intermediate region in which the particle rattles in the cage. Okay, So Mock coupling theory, I'm not entering into this theory, makes precise prediction about the behavior of this correlator, this density correlator in the Qt space. You have a power law in entering the plateau with A up as an exponent, a power law in going out of the plateau in exit the exponent. These exponents have precise limits. And then you can fit with the stretched exponential this part and get relaxation time that has to go with the a power t minus tc to the gamma, and a, b, and gamma are related. So what happens is this. We have, let me explain it better, what I have said so far. We have, no, I jumped, sorry, this is the explanation. So we have the self-intermediate scattering function, which is the Fourier transform of the density-density correlation function of a particle with itself. And you have a short-time regime, which is ballistic, and this is Gaussian. Then, forget this boson peak, superstructure, we're not interested. Then you have the rattling in the cage, so short-time ballistic, intermediate time rattling into the cage, long time going out of the cage, so random walk, like the Brownian regime as predicted by Einstein. At high temperature, you just go from ballistic to Brownian. So this is exponential. At low temperature, when you have the glassy dynamic, this is stretched exponential. So you can I can calculate this correlator with molecular dynamics, and I can fit it to this function, so that I will have the relaxation time of this slow dynamics, the exponent of the stretched exponential, and also the relaxation time of this fast ballistic dynamics. Okay. Then, when I look at the slow relaxation time, I can see that there is a transition from a behavior that is, let's say, fragile. It change behavior from a fragile behavior to a strong behavior. This is due to the fact that after a certain temperature, the cages are frozen, and the particle can only hop outside the cage with a thermal fluctuation. Okay, so this is an extra transition, but I'm not sure I will have time to talk about that. So let me just finish showing two things. One is this is the correlator calculated for water. This is another potential similar to the other, an older one which we used back in the days, the SPC. So you see these are the f of qt calculated out of the trajectory of molecular dynamics. And this is the relaxation time extracted here. That is, at the beginning, the relaxation time of the cage and behaves according to Mock coupling. And then here, changes trend and is due to hopping. It's still a relaxation time, but it's due to hopping phenomena. So we can see also the difference between these two phenomena. So water is becoming as a common gas transition, but there is also an interesting fact, which is that this crossover from fragile to strong happens exactly on crossing the Widom line. So the dynamic crossover happens on the Widom line, or very close to the Widom line. This has to do with the fact that the Widom line separates region in which the fluctuations are more high density from a region in which the fluctuation of low density prevail. And when you have high density or low density, you have also a different dynamics. So this crossover in dynamics is related to this particular thermodynamic feature for water. So I don't have time to talk about the hydration water. Just let me tell you that, and then this is my last thing. We studied also hydration water over cooling. This has to do with the cryopreservation. So you can, you have to avoid freezing when you want to preserve organs, for example, or also stem cell. It's important to avoid freezing. And for doing that, since water has this strong tendency to crystallize, you put stuff in water. you put, for example, you put dimethyl sulfoxide, which is very cytotoxic but very effective. But since it is very cytotoxic, in order to diminish the quantity of dimethyl sulfoxide, the people use disaccharides, saccharides, carbohydrates, maximum disaccharides in general. And so I studied also lysozyme in water and lysozyme in water and trehalose. And I did study in particular this correlator that I showed you, the density-density correlator, only for hydration water, to see how water was behaving close to the surface of a protein with and without trehalose. And we saw, let me cut a very long story short, and we saw that trehalose is able to slow down very much the movement of the proteins. And we think that the cryoprotecting characteristic of trehalose are related to that. So we studied that relaxation time, and we saw how it was changing when we had only water close to the surface of the protein and water and trehalose close to the surface of the protein, and related this to the cryoprotective behavior. I saw a transparency that I wanted to show you, but where is that? Okay, so this is the take-home message, and with this I finish, of the results that we found. We saw that when water hydrogen bonds to another water molecule undergoes the alpha relaxation, which is this relaxation of glassy dynamics, but when it hydrogen bonds to a flexible macromolecule, it has another relaxation, which is not the cage relaxation, that hinders the protein motion. And this happens below a certain temperature, which is called the protein dynamical transition. So we think that this particular temperature that was discovered for protein has very much to do with the properties of water. These are the correlators I told you about with bulk, hydration water, and lysozyme water. And we fitted that to the structured exponentials and two different relaxation, because we have an extra relaxation here. But since my time is over, depending on the audience, I could finish. Oh, that was another thing. That is the brine rejection. Let me show you. This is an off-equilibrium simulation. This is a crystal growing with the NaCl, and the crystal is growing and excluding, is excluding the ions. This is the brine rejection. This is for the icy moon. This is a study that we do for the icy moon of Jupiter. You see, and this is the brine. We did it for several crystals because we don't know what will be the pressure and temperature condition of this icy moon. So it may be ice H, which is the ice you see, or maybe another kind of ice. Okay, this is just for fun at the end, because I don't have time to go into details of these other studies. Just let me conclude that water has many anomalies in the supercool state, and is often in solution, and in several cases also in the supercool state in nature. And this anomaly matters also when water is in solution. And molecular dynamics simulations are particularly important in this context, as they can help experiments to reach the proper points and also to extrapolate behavior where experiments cannot go. Let me just acknowledge my recent collaborators. Paola Francesca, Leonardo Verina, and Lorenzo Tenuzzo are and were previous PhD students of mine. Paolo now is a postdoc in my group, actually. And then Maria Martin Conde is now the associate professor at the University Polytechnic of Madrid. Benjamin Ramirez was a postdoc of mine. And then I have colleagues at Roma 3, Gaia Camisasca, Lauro Lupi. Mauro is now retired. There was a friend of mine of a long time. We collaborate for a long time. Let me also acknowledge a special collaborator and long-time friend, my professor at MIT when I was a postdoc. We kept on collaborating and became friends along the years. Unfortunately, he was old and passed in 2021, but let me just acknowledge him, especially, because he was also a dear friend. And I wrote a book on liquid state physics, and it offers self-contained treatment of the physics of liquid and with a statistical mechanic approach. It's written for graduate students and active researchers in the field. If you want to make a course, some colleagues of mine told me that found it most useful. And let me give you also an announcement. I organize a congress on water under extreme condition every other year since 2009. The first 3 editions were in Secam, but I moved the congress to Roma 3 from 2015. We jumped it in 2021, sadly, because of COVID. And next one should be in the summer 2025, although I'm not 100% sure because I might be in sabbatical, then I will move it a few months, but stay tuned. And I think that this is it. Thank you very much.
Thank you very much. Okay, we have already one question.
Thanks for the interesting talk.
Thank you.
Let me ask you something. You mentioned several anomalies of water, of course, and it was not clear which of your results were anomalous in the sense that which of the results that you were showing you do not expect, and it's very different from what you expect for other kinds of liquids.
Yes, water has this maxima of isothermal compressibility and of specific heat that other liquids do not have, because other liquids do not have a second critical point. So at the beginning, at the end of, at mid the last century, experimentalists tried to supercool and saw that there was this increase of thermodynamic quantities that was anomalous with respect to other liquids. And I thought they were divergent. But now we know that they were maxima. It's only that they couldn't reach experimentally that point. And that these maxima are the Widom line. So they show that there is a maximum of correlation length very close, and that this correlation length is pointing to a liquid-liquid critical point still in the one-phase region. So these are the anomalies. The other anomalies is the temperature and maximum density that has less to do with the liquid-liquid critical point. Water has many anomalies. There is a site of an English guy who keeps on updating them because they keep on finding them. It's very nice, but for my sake, these are the anomalies I am more concentrated on.
Thank you.
Sure.
More questions?
So how do you distinguish supercooled water from ice on, for example, on Mars? How do you know it's supercooled and not ice?
Right. This is a question for the experimentalist, of course, that others might have done. No, water, because they do the electric measurements. They're pretty sure that it's water, but the problem is it a pond of water or these micro pieces of water? Okay, they have done a lot of explanations saying that it's a pond. They succeeded in publishing a science, so I trust them, but of course it's not my measurement. It's experimentalist, so yeah.
Okay, another question is, when do quantum effects become relevant, or do they become relevant in water? Or?
So, water quantum effects are relevant if you want to measure quantities, for example, like the polarizability. If you want to calculate with molecular dynamics the polarizability of water, you need to go quantum. For example, there is the group of Giulia Galli, that is now Giulia is in Chicago. She's a huge group, and she comes from the group of Parinello, and originally many years ago, and she studies the properties of water with quantum mechanics. And there are several properties in which it's important to use quantum mechanics. But this one is not so crucial. For example, a lot of studies of water also with quantum mechanics are done now with the group of Roberto Carri in Princeton. But all these people using density functional theory now start to do this machine learned potential. This is the new frontier, because Otherwise, you need millions of core, and not everybody can accept millions of core. So they are now preparing for us this machine learning potential. The problem is, there are two problems. First, the machine learning potential is not so fast like this in any case. At least you need to calculate on, you need a lot of processor in a cluster. You can do it with a cluster, but it's much slower. Let's say maybe at least one order, maybe two. We are trying to test one, probably 2 orders of magnitude. So you have to do an entire 5 gram of that. But the main problem so far that I understood from them and also from Stefano Baroni, with whom I'm collaborating on these things on Mars, and they are doing the machine learning potential for us. So learned from quantum mechanics, that's not so transferable, because if you use a limited set to train the machine learning potential, then you can transfer the machine learning potential only very close to where you fitted it. So if I want to do an entire phase diagram, I would need so many ab initio simulation to produce the machine learning potential that it's better to do the simulation quantum, but it's impossible. So I'm not sure that this kind of problem will be solved in a short time. And then something else is so there are properties in which you are forced to go quantum, other in which may be desirable, but as you know, in the FT you also have a lot of approximation. So also there you do some mistakes. So now there is the physicists with this Paisani that is doing a good, apparently is very proud of it. He said this is producing a wonderful potential from first principle. And he says he's looking for the liquid critical point. So let's see. If he finds it, it means that it's transferable enough. We stay tuned.
I have a curiosity with regard to the last video you showed. So I remember that Antarctic ice is very pure at if you dig sufficiently down. So is it related to this fact that you mentioned that the sodium chloride, for instance, is expelled?
Yeah.
So
yeah. The phenomenon of brine rejection is present on our poles, and so iceberg, brine rejected, but they made large veins. So they are formed with brine rejection, and so they are inside. They have empty veins, because once the brine rejection is finished, then the liquid, which is the brine, melts, goes away, goes in the sea. And so the iceberg has all these veins, empty veins inside that make the structure more stable. So actually the brine rejection is important also for for the stability of the iceberg. And then, as you say, of course, it's more pure because it excludes the ions. The percentage of ions contained in it is very small. Sure.
More questions?
Thanks for the lecture. And I'm curious if there is a way to theoretically calculate how fast you have to cool water to make it to take it to the supercooled state. If there is some way to do that.
Probably there is, but there's no purpose, meaning that they are trying to cool as fast as technology can allow them. For example, the group of Anders Nilsson in Sweden is producing small droplets of water, okay, and sending X-ray on those small droplets, supercooled. And sometimes these droplets crystallized, but when they do the scattering, they see the peaks. So they take away those results. Some of these droplets do not crystallize, so they use those results for their results. You understand? So I mean, it's easy, as much as we can. It's still not enough. So maybe if you calculate it should be more. But nucleation time, in any case, is calculated also by simulation. There are a lot of studies on this. but no, I never did it.
Yeah, I have a question about the self-correlation function, and perhaps it's related to what is on the board. Is that so? You have your particle and you have your cage, right? So it will start bouncing, and your self-correlation function will like oscillate because you have like a probability to come back. But when you jump from one cage to the other one, you have still this kind of probability of coming back. So the correlation function should not have like a one plateau, then decay again, and having a smaller plateau, and decay again, and a smaller plateau. So have like many plateaus. Why just one?
No, it's just one, because it's a length scale. When you look at the long time, you look only at the phenomena that happens on that long time. You look at the correlation between yourself in zero and yourself after a long time. After a long time, you're escaped in the cage anywhere.
Okay, so
anyway.
In other words, so that self-correlation is you average over many realizations of your...
yes,
okay.
Exactly. And there is no privileged origin of space-time.
More questions? Okay, if not, we can thank Paola again.
Thank you. Thank you very much.